Welcome back to ECE 442-542. What I want to do in this B session of today is to try to finish up example number 4 that we've started several times. And in this session, I want to illustrate example 4 as if it was a PI control problem, and we're trying to do this design process using the root locus strategies that we are learning. And in particular, that means how do we find K, or what is the range of K for stability, just to sort of get us started on that path. In this particular problem, then, we can identify the generic transfer function that we want to be sketching the root locus for, and anytime we say locus, then that's telling us that we are playing this game and we need to identify the poles and zeros on our z-plane plot that we are going to be sketching the root locus for. We have, in this particular system, we have a pole at 1 and we have another pole at -2, and the pole at 1 is due to the PI controller. The pole at 2, we're starting with an unstable plant, and we need to do something to stabilize it. It's not going to be stable in the open loop case. And we have a 0 at 1/2. Now that we have the poles and zeros on our playing field, now what we want to do is start sketching the root locus. One of the first questions you should ask probably is what real axis line segments are on the root locus, and that should just be coming very quickly to you. We now look at each segment that exists and count how many poles and zeros are to the right of that segment. Doing that, we find then that we have these two segments of the real line that are belonging to our root locus. We can then start asking, okay, what's the pole zero excess? How many branches do we have? We have two branches of the root locus because we have two poles. These two are going to go towards each other between z = 1 and z = 2, and they are going to collide and then break away. And what happens thereafter depends on what else is in the playing field, or what other x's and o's or poles and zeros we have. In this case, we have another line segment that they must be going towards, because there's a zero, a finite 0 at 1/2, and because of our pole zero excess of 1, we have an infinite 0 at -180 degrees. A potential exam question that I could ask pretty quickly without you having to sketch much are the following. Where is the breakaway going to occur, if it does occur? And in this case, we do have one real line segment between 1 and 2 that contains two branches of the root locus, and so we know that there has to be a breakaway there. Now, where that goes after the breakaway is going to be influenced by the pole zero excess and the number of finite zeros we have. In this case, the breakaway is going to occur between z = 1 and z = 2, and so we're going to have these two colliding, and it may not be centrally between 1 and 2. These may approach each other slightly at a slightly different rate, and they may break away closer to 1 or closer to 2, and that's going to depend on the other poles and zeros distributed around those two in question. But once we find the breakaway, then for this particular pattern of two poles on the right of a single zero, and that's all that you have on your pole zero diagram, then once we've found that breakaway point, we can use that distance between that breakaway point and the zero to form a radius of a circle, and that radius will then determine, I'm actually sort of drawing this backwards from what you might think needs to be drawn, but now these two are going to approach each other. They're going to meet and break away. Then they will actually re-enter, and there will be a relative minimum at the point of re-entry. One will then go towards the finite zero, the other will go to the infinite zero, and that's the pattern or the picture that we have. Now let's see if we can find those, and the re-entry then, let's just answer that question. The re-entry is going to occur between z equal a half and z going off to minus infinity. Or you could have said z between greater than minus infinity and less than 1/2, and here you might have said z is living between 1 and 2. That's another way of expressing those two, or answers to those questions. In order to find those breakaway and reentry points, the breakaway occurs at a relative maximum between the two poles. And it's a relative maximum of the gain k that we're using to vary to create our root locus. To find the breakaway point, we can rely or use the magnitude condition. And for this, in general, it's this k g bar of s magnitude needs to equal 1. For our particular system here, and for a non-negative value of gain k, we have k times the different terms magnitudes on g bar of s. We have the zero factor, we have the pole factor due to the pole at 1, we have the other pole factor due to the pole at 2, and those now have to equal 1, which we can now solve for k by multiplying through in the appropriate manner. And we now have k is going to be this magnitude of the pole factors divided by the magnitude of the zero factors. If we actually had some additional gain up here, let's say gamma, then that would have to occur there in the expression for the gain k in our root locus sketching process. Now that we have this magnitude, now we're in a position to actually find this either via an analytical derivation, but a lot of times it's easier to just find that numerically. So let's now find the relative maximum of k, and we already know where that's supposed to occur. It's going to be between z equal 1 and z equal 2. So let's find the relative maximum of k between z equal 1 and z equal 2 numerically. And let's just go to our calculator and see if we can now do that with the calculator. Here is our TI Inspire, and now what I want to do is I want to actually find, let's say, the absolute value of different terms, which is really just the expression for k that I've identified here. So now I have the factor z minus 1, and I have the factor z minus 2. Those are my numerator factors due to the poles. And then downstairs, I have my factor due to the 0. And that's now the expression that I want to be using, but I actually want to evaluate that at different values of z and try to find a relative maximum. So I can actually go and copy that down and just say I want to evaluate that expression. So there's my vertical bar when z is equal to, and for no better choice, let me just say, well, let's look halfway between that, and let's say we look at z equal to 1.5 and find the gain k, and we get a value of gain k of 0.25. Meaning now what I'm doing is I'm looking at really a table of values of z and what the resulting gain is going to be. In this case, we said, oh, at z equal to 1.5, that produced a gain of 0.25. If I go back and I say, okay, let me do that again, but let me say that now we maybe expect the breakaway to be closer to the point z equal 1 because we have a 0 on its left. And now we are getting bigger. So we have increased our gain k from 0.25 to 0.266, and let's now write that down. Meaning at a value of 1.4, we now have a value of gain k of 0.267. Well, it's going in the right direction, so let's look at what we get if we said, well, z is 1.3. And now actually we're going smaller again, so somehow we've gone through this relative maximum between 1.4 and 1.3. Here we are at 0.26, whatever it was, 25. So let's just look at 1.35, halfway between 1.3 and 1.4. So I'll add another significant digit to z equal 1.3 to become z equal 1.35. And now we have 0.2676, which is bigger than what it was at 1.4 and what it is bigger than at 1.3. So we are converging, and if you're sketching this, your sketch is not going to be any more accurate than 100th decimal place, so that's probably accurate enough. But let's just look at some more points since we are doing this without much effort. Let's go ahead and look at halfway between 1.35 and 1.4, sort of, and say that's 1.37. That's now 0.2679. And that's bigger than we were at 1.35. If we look at 1.38, now we're actually getting smaller than we were at 1.37. So this is 0.2677, I believe. And if we looked at just one more point, let's say 1.36, just to see if that's any bigger than 1.37, because we sort of went towards 1.4 and now we want to go back to 1.35. So now if we go to 1.36, and again, you wouldn't have to do this on an exam, and probably for practical purposes of sketching, you're not going to need this much accuracy. This is now 0.2679. And if we were to compare 1.36 to 1.37, we're looking at a little bit bigger number at 1.37. So in that case, here is our relative maximum. In this case, we can now say that we know where we are going to be a maximum at the breakaway. This is now, this point is going to occur at 1.37, and we know the gain to get us to that point. We we now know we will be at z equal to 1.37 with k equal to 0.26793, if we remember that fifth significant digit from our calculator computation. We now can use that breakaway location of z equal 1.37 to establish a radius between that point and the 0, which is acting as the center of our circle. Our 0 is at 1/2. We now can say that we have a radius equaling 1.37 minus the 0's location of 1/2, or now we know the radius is about 0.9. It's now 0.87. If that's the radius of our circle, now we know exactly where our re-entry point is, because we can follow that circle all the way around the center of that circle at 1/2, and now we're going to re-enter at 1/2 minus 0.87, or now we are going to be re-entering at minus 0.37. And what's the value? So now we can say this point right here for re-entry is going to be z 0. Or minus 0.37. We can plug that value into our gain k, where our gain k was this z minus 1, z minus 2 over z minus 1/2 at z equal minus 0.37. And we've got the calculator there, so let's just use that. We now want to find what it's going to be gain-wise at minus 0.37, and we find that we now have a gain of 3.732. When we re-enter the real line. Let me just reiterate what we now have sketched. We've now sketched a root locus. This is now the final root locus sketch for that particular system. It consists of two real line segments that have two branches on them each, and those are connected by this circular root locus shape that breaks away at z equal 1.37 and re-enters at z equal minus 0.37. Let me just write down what we are seeing for this particular pattern. The unique structure of the root locus let's just say the unique structure of this problem, which the structure is two poles to the right of 1, 0. That's the structure that I'm referring to. The root locus has the circle shape between the breakaway and re-entry. Now, what we want to do is actually find the minimum value of k for stability. We know where it should be in terms of a value. We know that it's going to be at that triangle location, and the maximum value of gain for stability is going to be, let's say, at the square where that second branch exits the unit circle out of -1, and we want to know when do we first get both of those branches into the unit circle. That's going to occur when our root locus shape actually intersects the unit circle, and we want to see if we can find that analytically and not via trigonometry. So let's now find the minimum value, and we know that it needs to be between two values. We know it needs to be between or bigger than 0.268 and less, well, yes, and less than 3.7. It's somewhere between those two values, the breakaway and reentry. We know it's between those two values of gain, K. So now let's see if we can actually find that minimum value of gain, K, to get us into the unit circle, which is indicated by those triangular shapes. So our minimum value of K for stability is what we're looking for, and we want to go ahead and see if we can find that analytically. Our picture again, just to remind us, we have our root locus, we have it breaking away and then re-entering. And it's actually going to correspond to the location associated with those triangles. And just to give us something to, whoops, let me change the color so we don't get that confused. Let's say that we call this point Z triangle. Maybe we call that, or we know that it's going to have a value of a real part of A and an imaginary part of B. What do we know about the relationships that exist for this particular system and this root locus pattern? First is we know if we have those Z delta values, we can write a characteristic equation if those are the actual closed loop poles. Or what is the characteristic equation when Z is equal to Z delta? The characteristic equation is going to be made up of Z minus Z delta. That's one factor. And we'll have another factor with its complex conjugate. If we now multiply that out, we get Z squared. Then we will have Z delta times Z and Z delta star times Z with minus signs. And then we have plus Z delta star. Now we simply need to remember some relationships about complex numbers. If we add a complex number and its conjugate, that really just gives us 2 times the real part of that complex number. And if we multiply a complex number by its conjugate, then that actually is just going to be the magnitude of that complex number's value squared. Now, we just said that we were going to be using or labeling Z delta as A plus JB. Well, now we know what the real part of Z delta is. That's just A. And we know what the magnitude of that complex number is squared. That's just A squared plus B squared. So now we know that this characteristic equation at the point Z delta and its twin Z delta star, that's going to give rise to a characteristic equation of Z squared minus 2AZ plus the magnitude of that complex number, which is squared, which is A squared plus B squared. And that's really just the distance away from the origin, and we're squaring that, so that's the hypotenuse squared. That's one relationship that we know. We can identify that if we have labeled those points, Z delta, to occur at A plus JB, then they will give rise to a characteristic polynomial of z squared minus 2az plus the magnitude of that complex numbered squared. A second relationship is because we only have two poles, and those two poles are actually on the unit circle, we know something about the radius of those pole locations. We now know that another relationship is we have z squared minus gamma z. Let's pretend we don't know what the linear term is, plus 1. We know that they are a distance of 1 away from the origin because those points are on the unit circle. All of our roots are on the unit circle. That's why the constant coefficient is 1. If we had 3 poles and 2 were on the unit circle and 1 was not, then this constant would not equal 1. It would basically equal the product of all 3 of those, which would be influenced by the third coefficient or the third root. But this constant coefficient, because it's a second order and we only have the 2 complex conjugate poles, this constant coefficient is 1. That's a second property. A third property is we can now write down the characteristic polynomial of our closed loop system in terms of the feedback gain k. Meaning we have 1 plus k g bar of z, and that's equal to 0 in our characteristic equation. The characteristic polynomial is this piece. That's now 1 plus k times z minus 1 half over z minus 1, z minus 2 for our particular problem. That's equal to 0 to give us our characteristic equation. We could now say, oh, let's now from this put that or look at the numerator of the resulting equation, or we now have z minus 1, z minus 2 plus k, z minus 1 half over z minus 1, z minus 2 equaling 0. If we look at the numerator, we now can say that we're going to end up with z minus 1, z minus 2 plus k times z minus 1 half, and that's the expression that's going to govern our dynamics. And this is now our characteristic polynomial. If we then clean that up a little bit, we can say that this piece is going to be z squared minus 3z plus 2. This piece is kz minus 1 half k. And if we combine all of those together, then the characteristic polynomial will be z squared minus 3 minus k times z plus 2 minus 1 half k. Those are our 3 properties. We have a characteristic polynomial in terms of k. We have a characteristic polynomial, some of the coefficients known because we know the roots, all of the roots are on the unit circle. Our constant coefficient is 1. And we also have this expression just by assigning those 2 complex conjugate poles to be at A plus and minus JB. We have that red boxed formula, we have that red boxed formula, and we have this expression. Those are relationships that we know are true. Now, the consequences of those relationships, or basically using those, and we know that they have to be simultaneously true. We know that if we look at the first two, we can say, oh, we know a relationship between the real and imaginary part of z delta. They have to have a magnitude of 1. So now we know that a squared plus b squared is equal to 1. And what else do we know? Well, if we look at the third relationship and equate coefficients there, and in particular the constant coefficient with the constant coefficient in the second relationship, we also know that we have 1 from the second relationship's constant, and that's equal to 2 minus 1/2 k. And now we can solve this for k. We now have 1/2 k is equal to 2 minus 1, which is 1. Or if we now solve that for k, we see that k is equal to 2. And this is actually a piece of the information that we needed. This is the value of our gain, k, that we can crank up. We knew it had to be, just based on this information that we already had from our breakaway and reentry, we knew it had to be bigger than 0.27 and less than 3.7. And now we're finding that it's actually equal to 2. So this is the value of k at z equal to z delta. So now we know k, and we have all of these other relationships that we can use. Now we can say, well, we know that z squared minus 3 minus k z plus 2 minus 1/2 k is equal to z squared minus z plus 1. That's by using k equal to 2 in those coefficients. So we now get z squared minus z plus 1. That's by replacing k with 2. Now, we have the exact characteristic polynomial, z squared minus z plus 1, and this first equation allows us now to solve for a and b. If we compare this with z squared minus 2az plus a squared plus b squared, comparing the z to the 1 coefficients, we can now say that, oh, 2a is actually just equal to 1, or a is equal to 1/2. And from the z to the 0 coefficient, we now know 1 is equal to a squared plus b squared, which says b squared is 1 minus a squared, or b is the square root of 1 minus a squared. But we know what a is. A was 1/2. That's the real part of z delta. We now know that this is 1 minus 3/4, or I'm sorry, getting ahead of myself, 1 minus 1/4, which is now the square root of 3/4, or b is now the square root of 3 over 2. We now know then that z delta is 1/2 plus j square root of 3 over 2, and that is going to be z delta when k is equal to 2. This is now the minimum value of k for stability. And what's the maximum value? Well, we hope then that the maximum value is going to be what's going to happen at these squares. So it's going to be very hard to find the square inside or between the re-entry point and z equal to 1/2, but we know exactly where it breaks out of the unit circle or goes unstable, and that's when z is equal to -1. And we have the formula for k, so we can use that to find the maximum value of k, and that's when z is equal to -1. From our formula then, we have k at z equal -1 is z minus 1, z minus 2, all over z minus 1/2, all of those with absolute values. That's when z is equal to -1. We get -2's absolute value, that's 2. We get -1 minus 2, or 3, -3's absolute value, that's 3. We have -3/2 below, and we take its absolute value. And now the 3's cancel, the 2 downstairs in the basement of the downstairs comes up, and we see that k is equal to 4. And that's now our maximum value, and that's when the root locus, the second root of our root locus, will escape and go unstable. And we now can conclude then that we've found the range of k for stability. K needs to be bigger than 2 and less than 4, and that's going to then provide the range of k for stability. And hopefully then, if you wanted to, you could pick a k between 2 and 4, and you might want to pick it so that you are still in, for the first quadrant, maybe what you would want your value to be for a closed loop behavior, maybe you want it to be somewhere in there. And that might be your desired dominant poles. You could then find the radial distance at that value of gain k. So you're looking at a gain of k a little bit bigger than 2, and it's not going to probably be all the way over to be 2 negative real roots, which is at the 3.7 value of gain. You'll want to be a little bit less than that probably for an acceptable transient performance behavior, but you will have zero steady state error because we started with a PI controller which forces the open loop system to have a pole at z equal 1. I hope that that helps you understand what might happen in a configuration like this, and in particular maybe some of your homework problems.